Hi everyone. In this lesson we're going to take a look at an approximation technique for the definite integral called Gaussian quadrature. So consider a definite integral from a to b of some function f of x, and what we want to do is we want to try to approximate this by writing it as the summation of the function values f of x evaluated at certain nodal values x1, x2, x3 out through xn times some coefficients c1, c2, c3 out to cn. So, instead of trying to find an antiderivative for f, all we have to do is evaluate f at certain values, x1 through xn, multiply those values by the coefficients ci and sum. So we want to find these ci's and xi's so that this is a good approximation technique. So to do this, here's how we're going to handle it. We're going to try to find the xi's and ci's so that this integral is exact for all polynomials of degree 2 times n minus 1 or less. Alright, so to start our Gaussian quadrature technique now, consider this definite integral. Now notice we're just going, the a is negative 1 in this case, and the b is 1. So we're just going to consider the approximating from the definite integral from negative 1 to 1. We'll generalize that to a and b later on, after we figure out what the x's and c's are supposed to be. Now, so suppose we just want to do something pretty simple here. We just want to say that this definite integral is going to be approximately equal to c1 times f of x1 plus c2 times f of x2. So the little n in this case is 2. Now to figure out what the x1, x2, c1, and c2 are supposed to equal, what we want is we want this approximation technique to be exact for all polynomials of degree 3. Notice the 3 comes from 2 times 2 minus 1. This is the little n right here in this case. Alright, so to find out what the x's and c's are, notice this first. Integration, the definite integral, is what we call a linear operation, meaning that if I have the integral from a to b of c1f plus c2 times some function g, I can split this definite integral up like this over here. So notice how we just distributed the integral and then we factored out the constants. You can certainly do that. So because of that, the definite integral is what we call a linear operator. Now, in particular, for polynomials of degree 3 or less, notice right here we have the definite integral from negative 1 to 1 of a polynomial of degree 3 right here, and we can break it up like this down here. So notice we just distributed the definite integral among each function here, and then we factored out all the constants. So we have a3 times the integral from negative 1 to 1 of x cubed plus a2 times the integral from negative 1 to 1 of x squared, and so on. And the last term is a sub 0 times the definite integral from negative 1 to 1 of just 1 dx. Alright. Now what we want is we want equation 1 to hold exactly for all polynomials of degree 3 or less. Now remember that's this one right here. So we want this equation here to be exact. We want that to be equal, an equality, when our function f is a polynomial of degree 3 or less. Now because of these two properties right here, because of this property right here, it suffices to show that that equation holds just for the polynomials 1, x, x squared, and x cubed. So in other words, what we need to do is we need to show that this holds, so we need to show that this equation holds where we have equality right here when f is the polynomial 1, x, x squared, and x cubed. If we can find the x1 and x2, c1 and c2 that do that for these four functions here, then this equation will also be true for any polynomial like this right here, because we'll be able to just break this definite integral up like this, and then if our equation is true for x cubed, x squared, x, and 1 individually, it'll be true for this one as well. So that's what we want to do. So what we do then is we just plug the function 1 into our equation up here, into number 1. Move that down a little bit there. So we just plug into this equation right here. We'll put equality right here. And if f is the constant function 1, what we get is the integral from -1 to 1 of 1 dx. That should equal c1 times this right here is f of x1. Notice if f is a constant function, f of x1 is just 1. And plus c2 times f of x2. Notice this is f of x2 right here. Alright, so we get this equation, and notice that the definite integral from -1 to 1 of 1 is 2. And so we get this equation. 2 equals c1 plus c2. Alright. Now, when we plug x into equation number 1 up here, what we get is this, the integral from -1 to 1 of x dx. Well, that's just 0. So that's supposed to equal c1 times x1 plus c2 times x2. Notice that the x1 right here is f of x1 when f is the function x, right? And this right here is f of x2 when f is just the function x. And the integral from -1 to 1 of x is just 0. Then when we plug x squared into the function f up here, what we get is this, the integral from -1 to 1 of x squared dx. Now that's going to be 2/3, and that's going to equal c1 times x1 squared plus c2 times x2 squared. Once again, notice that this is f of x1 when f is x squared. And the same thing right here with x2 squared. And then when we plug x cubed in for f up here, we get this, the integral from -1 to 1 of x cubed dx. Now that's going to be 0. And that's equal to c1 x1 cubed plus c2 x2 cubed. And once again, this is f of x1 when f is the function x cubed right here. Alright, so what we end up with now are these four equations right here. Notice we have four unknowns, c1, c2, x1, and x2, and so we need four equations, and that's exactly what we ended up with. And they're just rewritten down here for us. So right here are the equations just rewritten for us. And so we need to solve these four equations for c1, c2, x1, and x2. Now let's notice that for this problem up here, in order to solve these equations, there's a certain amount of symmetry to this. You know, we're integrating from -1 to 1, and the functions that we're looking at are 1, x, x squared, and x cubed. The 1 is an even function, x is an odd function, x squared is even, and x cubed is an odd function. So it sort of makes sense that the x1 and the x's and c's are going to have a certain amount of symmetry themselves. So it makes sense that if this is x1, then this is going to be x2. So x1 is going to be the negative of x2 and vice versa. They should have a symmetry about the origin. And the c's should also have a symmetry. Remember, the c1 goes along with the x1 and the c2 goes along with the x2. So it makes sense that the x1 will be just negative x2, and it seems reasonable that the c1 should equal c2. Now it's not going to be the negative of c2, but they will be equal to each other. Now notice if we make this assumption and we plug substitute that into the first equation right down here, we get that 2c1 equals 2, so that implies that c1 equals 1, and that's also equal to c2. So, it seems like the c1 and c2 should be 1, but let's verify that we can solve the other equations for the x's. Now, if we make this assumption here, what we get for the x1 is that we then get the second equation down here becomes x1 minus x2 equals 0, and plus x1 plus x2 equals 0. Or if we substitute in x1 being negative x2, we get x2 minus x2 equals 0. Well, that doesn't really tell us anything. Okay, so that equation doesn't give us much. Now if we take a look at the third equation here, what that tells us is that x1 squared plus x2 squared equals 2/3. Notice I'm letting c1 and c2 be 1 here. Now, assuming this equation right here holds, that we have some symmetry, what we're going to get is 2x1 squared equals 2/3. Notice I substituted there x2 is negative x1. And when I square this, I just get x1 squared, because negative 1 squared is 1. We end up with this, which tells us that x1 squared equals 1/3. So x1 equals 1 over root 3. Now x1 is actually going to be a negative number. So actually, x1 is either going to be plus or minus 1 over root 3, so it's actually going to be negative, because I'm assuming x1 is less than 0 in this picture up here. So x1 is going to be negative 1 over root 3, in which case then x2 from the same equation right here, we would also get 2x2 squared equals 2/3, which would imply that x2 squared equals 1/3, which implies that x2 is positive 1 over root 3. Okay. Now, alright, so we've solved for our c's. We should also check that the third equation actually still holds. We didn't use it. Let's make sure it still holds. So if c1 is 1 and c2 is 1, notice I get there x1 cubed plus x2 cubed. That had better be equal to 0, or else our solutions up here are not valid. Well, yeah, if I plug negative 1 over root 3 in here for x1, I get negative 1 over 3 to the 3/2. And if I plug 1 over root 3 in for x2, I get plus 1 over 3 to the 3/2. And yes, that does equal 0. That checks out. Alright, so we've solved our equations down here. We've gotten that c1 and c2 are both 1, x1 is negative 1 over root 3, and x2 is 1 over root 3. And that's summarized down here in these equations. So right here, c1 is 1, c2 is 1, x1 is negative 1 over root 3, x2 is positive 1 over root 3. So by choosing those values, equation 1 will be exact for all polynomials of degree 3 or less. Now let's use this technique with n equaling 2 to approximate the integral from negative 1 to 1 of e to the x dx. So what we're going to get then here is our function f of x that we're using is e to the x in this case. And so we have, this is going to be approximately now we found that our c1 is 1 and x1 is negative 1 over root 3, so this is going to be see the c1 is 1 right here, and the c2 is 1. And the function f is just e to the x, so we get our answer as being e to the negative 1 over root 3 plus e to the positive 1 over root 3. And when we evaluate that, we get 2.342696. So that's what we get for our approximation. And notice this is a really easy integral to evaluate anyway. Notice the exact value. Well, that's just going to be e to the 1 minus e to the negative 1 when you find the antiderivative of e to the x, which is just e to the x, of course. And when you evaluate this, you get 2.350424 approximately. And so you notice these two numbers, well, they're pretty close. So this is a pretty good approximation to the definite integral. Pretty good considering that we only used 2 node values. Now, when we developed this problem, we only used polynomials of degree 3, or the n was 2 in this case. If we go back to this formula up here, so notice for our starting problem here, the n was 2, and so we were just using this formula right here. Now, well, suppose we made the n 3, in which case the right-hand side here would become c1 f of x1 plus c2 f of x2. And we would want this to equal this quantity, the definite integral from negative 1 to 1 of f, for all polynomials of degree 5 or less. Notice that comes from 2 times 3 minus 1 is 5. And so we would want to have equality here whenever f is the polynomial or the function 1 or x squared, x cubed, x to the 4th, or x to the 5th. And if we plug each of those functions in, going all the way up to x to the 5th, we would get 6 equations and we would have 6 unknowns. Now notice the first equation would be something like c1 plus c2 plus c3 equals 2 still. And the second equation would be something like c1 equals 0. And then we'd have 4 more equations. And this would be an x3 right there. And we'd want to solve those equations for c1, c2, c3, x1, x2, and x3. Now notice that you still have sort of a symmetry here. You'd have 0, negative 1, 1. And so it makes sense that the x1, say the x1 is right here, the x3 would have to be an equal distance on the other side of 0. And it would make sense that the x2 would actually have to be 0. So x1 is negative x3, x2 is going to be 0, and then our c's are going to have a certain amount of symmetry to them also. The c1 and c3 are going to equal each other. The c2 is going to be something different, however. And so making assumptions like that, you'll be able to solve those 6 equations for c1, c2, c3, x1, x2, and x3. So in other words, making assumptions like c1 has to equal c3, x1 should equal negative x3, x2 should be 0. You'll be able to solve all of those four equations for the c's and x's. And when you do that, here's what you get. So we have a table down here. So let me just put that drawing back here. So what you're going to get, if you look at this table here, it tells you the nodal values, the x's are right here. So it tells you that x1 is actually equal to negative square root of 3/5. The x2 is 0 right here, that's your x2, and the x3 is positive square root of 3/5. So you see that symmetry, x1 is negative x3 and x2 is 0. And the c's, your c1 that goes with the x1 is 5/9, and your c3 is also 5/9. You see this goes along with your two x values right here, the x1 and x3. So c3 is 5/9. That's the way you read this table. And the c2, that's this value right here, that comes out to be 8/9. So that's how you read this table. And then, if you assume that the n is 4, what you get are these values. So looking at this table here, you see the x1 is going to be negative 0.86, and the exact value for that is given by this formula right here. The x4 is going to be positive 0.86 approximately. The x2 is going to be negative 0.34 approximately. The x3 is going to be positive 0.34 approximately. And then that 0, that's just there for reference. That's not one of our nodal values right there. And then the c1, c2, c3, and c4, the coefficients that go along with the f of x values, are going to be these numbers right here. So the c1 and c4 are both 0.347855, which come from this value right here. And the c2 and c3 are 0.652145, which are approximations to those two values right there. So that's how you read this table as you increase the number of nodes used for this approximation technique. So let's take a look at this problem now. So using this table, let's use Gaussian quadrature with n equaling 3 and 4 to approximate the integral from -1 to 1 of e to the x dx. Alright, so for n equaling 3, alright, so that's going to be then approximately, if we're using this information right here, it's going to be approximately 5/9 e to the negative 0.774597, or negative root 3 over 5, 3/5, plus 8 over 9 e to the 0, plus 5/9 e to the positive root 3/5. And let's see, that quantity comes out to be 2.35033369. And so, yeah, that's a little better approximation. Remember that the exact value was, just put that up here, our exact value, recall, was well, approximately anyway, from my calculator. 2.3504023887. And so yeah, this looks like a little better approximation comparing it to when we used n equaling 2 right here. Now let's do when n is 4, in which case we're going to get the integral from -1 to 1. Alright, now using all of these values down here, I'm going to use the approximations here instead of writing out these exact values here like we did previously. It was easy to write root 3 over 5. I'm just going to use the approximate values here. So we got our approximation over here being and so there you go, that's what we get. And when we evaluate that on our calculator, we get that that's approximately 2.350. So that's what we get when we evaluate this. And notice that that is a little better approximation to our actual answer up here than when n was 3. You can take the difference of these two values, this one minus this quantity, and this one minus this quantity, and you'll see that the error associated with this one is smaller than the error associated with the n equaling 3. Alright, so now let's take a look at this. For the problems that we looked at, we were just approximating the integral from -1 to 1. But of course, we might want to approximate the integral from a to b of f of x dx, where a and b are different from -1 and 1. So how do we do that? Well, what we can do is we can modify the formula using an integration by substitution technique. So let's notice this. If we start out with this integral, and we do a u substitution, say we let u equal. Now notice from this the du is going to be, or moving the 2 over b minus a over to the other side, we get like that. Now also, if we take this equation here and we solve it for x in terms of u, what we're going to end up with is that x equals we're going to end up with that. You can just check that out. Okay, just take this equation, solve for x in terms of u, and you'll get this. Now, doing all of these substitutions in here, we want to turn this integral into something that goes from -1 to 1. Well, that's exactly what all of these are going to do. So this integral right here, upon these substitutions, will then become, now, what does the a change to? Well, I have to plug the a in for the x right here. So just off to the side here, note that u of a, if I plug a up in here for the x, I'm going to get 2a minus a, that's going to be a minus b. So I'll get a minus b over b minus a, that's -1. And if I plug b in for the x right here, just notice that u of b is going to be, if I plug b right there for x, I'm going to get, the b's will cancel, one of the b's will cancel, I'll get b minus a over b minus a, and I get back 1. So this integral will become the integral from -1 to 1, f of, now I have to replace the x with all of this right here, so I'm going to get f of b minus a, and then I have multiply that by b minus a over 2 du, replacing the dx with this quantity right here. That's what we get. That's a constant. That can actually be pulled out in front of our integral symbol. So let's write all of this as. And then we get a du right here. And notice this integral goes from -1 to 1. So we can use our Gaussian quadrature to approximate this right here. All of it, including, we just throw the constant in. And then this will be is equal to this, so that's how we can use Gaussian quadrature to approximate an integral from a to b. We actually rewrite it like this down here. So let's take a look at an example. So here, for this example, right here, we want to use Gaussian quadrature with n equaling 2 and 3 to approximate the integral from 2 to 4 of e to the x dx. So we're going to use this formula right here. So now let's notice that my function, I'm just going to replace the u with the letter x. It doesn't really matter. Now the b is 4, the a is 2, so this is going to be 2x plus 6 over 2. And so that simplifies out to f of x plus 3. And so in this case, that's going to be e to the x plus 3. All right. So then what we have is the integral from 2 to 4. Now let's see, using n equaling 2, first of all, to start, using those nodal values, remember the c's are 1. x1 is -1 over root 3. x2 is positive 1 over root 3. We're going to get that this is approximately equal to, now remember I have a b minus a over 2 that has to appear out in front. So we're going to get b minus a over 2 being, oh well, that actually just turns out to be 1, right? 4 minus 2 over 2 times, and then I'm going to use my Gaussian quadrature to approximate the integral here. So it's going to be c1 times e to the, and what I have to replace for the x right here, -1 over root 3 plus 3, and then 1 times e to the positive 1 over root 3 plus 3, like that. And let's see, all of this, the coefficient here, the constant here, of course, being 1, all of this will evaluate out to being approximately. Okay, so rounding that to 4 decimal places, that's what we get for the right-hand side here. Now it's also interesting to note that the exact value, let's just put that up here, our exact is, of course, this of course is going to be e to the 4th minus e squared, and carrying that to 4 decimal places, that is 47.20909. So yeah, this is a pretty good approximation down here, considering that we only used 2 node values. Now let's do it for n equaling 3 and see what we get. Now let's recall that for n equaling 3 we have to use the coefficients right here in our table. We have to use all of these right here. Plus, and the x's are going to be 0, plus and minus root 3 over 5, root 3/5, and 8 over 9 and 5 over 9. For the coefficients, these are the c's right here. Even though the table says w's right here, those are actually your c values. Okay. So then going back to our problem here, what we're going to get is the integral using this function right here that we found. We're still going to have the 4 minus 2 over 2. Now it's going to be times 5 over 9 and there we go. Notice we have 5/9, 8/9, 5/9, and our nodal values negative root 3/5, 0, and positive root 3/5 that we're plugging into our modified function up here. And let's see, all of this will, when we evaluate this on our calculator, we get 47 point. And that's what we get. And you notice that this is closer to the actual answer right here than when we used just 2 nodal values. So this case right here was where n was 3. Right here, we get a much more accurate answer than we did when n was 2, which is to be expected. And that concludes our discussion about Gaussian quadrature.